Thank you very much. Thank you very much for joining us today, Ryan. For those of you who know a little bit about myself first, know that I do have a fairly powerful telescope and have a great deal of interest in astronomy. And a number of us have shown that there is a great deal of interest in astronomy among the group. So it came to me that I thought if we had somebody who could talk about the frontiers of astronomy, then it made sense to tap into the Carl Sagan Institute. So today with us, we have Ryan MacDonald, a research associate at Cornell University's Carl Sagan Institute. And he is currently preparing to analyze the first exoplanet observations from NASA's new James Webb Space Telescope. So with no further ado, I turn the meeting over to Ryan. Thank you for joining us, Ryan.
Thank you very much for the introduction and for the kind invitation to speak to you all today. And what an exciting time it is for us. So you mentioned just there that I'm working on getting ready to analyze the first observations of planets around other stars with NASA's new James Webb Space Telescope. And just earlier this week, we actually heard the official schedule of when the observations are coming down. So the first exoplanet observations will be taken on June 30th of this year, and the observations that I will be heavily involved with will be coming down on July 10th. So it's all going to kick off very soon. So in this talk, I'm going to talk a little bit about why we need telescopes in space, the particular science questions that we have not been able to address previously, that we will be able to address with the James Webb Space Telescope. And I'll also go a little bit into the engineering aspects of how this telescope will work, because it's quite a unique feat of engineering as well as a scientific mission. So, firstly, it might be worth looking into why we need to have telescopes in space, why we can't just accomplish all of our main scientific goals in astronomy and astrophysics from the ground. And in short, the main reason is that the range of wavelengths of light, colors of light that we can observe with our own eyes, is actually a very restricted range. And essentially the range of colors that we have evolved to be able to see correspond with the range of colors that our own atmosphere is reasonably transparent to. There is a wide range of other energies of light that are more energetic and less energetic than what we can see, that are reasonably opaque to us. The atmosphere of our planet obscures them. So this was really recognized decades ago, and in the 1990s, NASA launched a fleet of 3 so-called great observatories to study the universe beyond our own solar system in the colors of light that we can't see with our own eyes. Perhaps the most famous is the Hubble Space Telescope that has been operating ever since 1990 and observes the universe both in visible wavelengths of light, the infrared, and the ultraviolet. There was also the Chandra Space Telescope that is still operational today and focused on highly energetic phenomena in our universe, emitting X-rays, and until recently, the Spitzer Space Telescope that observed in the infrared. So when I talk about these wavelength ranges, here on this diagram illustrates the full range of energies that light has, the electromagnetic spectrum. And you can just see here that it's a tiny range in the visible that we can actually see with our own eyes. The Hubble Space Telescope can see the visible and a little bit either side of what we can see. So you can see a little bit into the ultraviolet and into the infrared. The Spitzer Space Telescope focused instead on much longer wavelengths, lower energy light in the near infrared and mid infrared, which enabled it to see through clouds of dust in space. And I'll show you some examples of that on the next slide. And the James Webb Space Telescope will essentially plug the gap between Hubble and Spitzer. And with its much greater collecting area and sensitivity, we'll be able to do things that were never possible before. So here are 4 real images taken by those existing space telescopes, illustrating some of the things about our local universe that we have already been able to figure out with space telescopes. So in the top left is an X-ray image from the Chandra Space Telescope of the Crab Nebula. So this is a remnant of an ancient exploding star. In the year 1054, Chinese astronomers saw what they described as a new star in the nighttime sky that then disappeared over a period of weeks and months. They didn't know it at the time, but this was a star exploding. And when a so-called supernova event takes place, it can briefly outshine an entire galaxy. These are some of the most energetic events in our universe. So what we're seeing in the top left is the leftover remnant of that star, a jet of high energy gas that is shining in X-rays coming out of the remnant of this long dead star. In the top right is an infrared image taken of a star called Zeta Ophicuri by the Spitzer Space Telescope. And what this illustrates nicely is some of the advantages of observing the universe at longer wavelengths than we can see with our own eyes, because this just looks like an opaque cloud of dust in visible light. But in the infrared, you can see through the dust to the star at the center, and you can also see this interstellar wind here. This is something called a bow shock. So if you go on a boat over a lake, for example, you see these ripples percolating outwards. Essentially what we are seeing here is winds of material from this star traveling outwards and impacting the surrounding medium between the stars. And as it does that, shining in infrared light. In the bottom left here is a visible image taken with the Hubble Space Telescope of another nebula, in this case, the famous Ring Nebula. So this is, again, a remnant of a supernova, in this case, a star that exploded 7,000 years ago and is about 2,000 light years away from us. And in the bottom right here is a lovely composite image that actually combines X-rays from Chandra, visible light from Hubble, and infrared light seen by Spitzer, all artificially colored here. So the blue light, the blue coloring that you're seeing here is X-ray emission from hot gas surrounding these two merging galaxies. The yellow color is visible light that you would see with your own eyes if they were sensitive enough to see this pair of galaxies. And the red here is infrared light from dusty regions where new stars are forming. So all of this is just to illustrate that we learn different information about our universe by observing it in different wavelengths. We have also been able to use space telescopes to peer much further back to much greater distances in our universe than those local universe images I was showing on the previous slide. And because of the amount of time that it takes light to reach us, the further back in space we look, the further back in time we look. This is an image called the Hubble Ultra Deep Field. This was formed when the Hubble Space Telescope stared at a single patch of sky for 25 days and just waited to see what it would see as it collected more and more distant light. And most of the objects that we see here are entire galaxies, each containing hundreds of billions or trillions of stars, with many of these galaxies going as far back as about 13 billion years ago. So the most distant objects in this image formed about 1 billion years after the Big Bang. So I've shown you all of these fantastic results from space telescopes that we have already launched decades ago. So why do we need another space telescope, and what will the James Webb Space Telescope be able to do differently? So it turns out that we can't currently see the very first stars and galaxies that formed in our universe. And the reason is that our universe has been continually expanding since it initially formed, blowing up like a balloon. And as the space that light is traveling through expands, it causes light to stretch out. It has the effect of increasing the wavelength of light as it travels through an expanding universe. So an ancient galaxy that was emitting high energy ultraviolet light, as the ultraviolet light has traveled towards us over many billions of years, it has stretched out and is now infrared light, even though when it was emitted, it was ultraviolet. And because Hubble can only see a limited region of the infrared, it can't see all the way back to the very first stars and galaxies that formed. So we really need a sensitive space-based infrared telescope to be able to understand what caused the first stars and galaxies in our universe to form. So that's one of the key science drivers for why the James Webb Space Telescope was initially developed. As far back as in the late 1980s, the concept was first being fleshed out. But it turns out that observing infrared light has many other scientific applications in almost every domain of astronomy. So looking at objects that we see around us, for example, just like the meerkats and crocodiles here, infrared light contains different information from visible light. So in the visible images that we see here, you can resolve some differences. You see that the meerkats have fur while the crocodiles have scales, but the colors are reasonably similar. If you switch, however, to the infrared, then we see a completely different picture, because the meerkats, as warm-blooded animals, positively shine in the infrared, while the cooler temperature of the blood in the crocodiles emits less infrared light. So this is just a conceptual picture to illustrate that we can learn something about the temperature of objects by observing in the infrared that we can't by looking at visible light. So in terms of applications to astronomy, here are 3 real images, the first 2 taken by the Hubble Space Telescope and the third taken by the Spitzer Space Telescope, showing the famous pillars of creation in the Eagle Nebula. So what we're seeing here is a cloud of interstellar dust, a region where new stars are forming. In visible light, we can't really see through the dust. But as you push to longer wavelengths into the near infrared, it's like a switch is turned, and we are much more sensitive to both nearer and more distant stars and galaxies in our universe, because we can see through the dust. And as you go further into the infrared, into the mid-infrared, you're then much more sensitive to the temperature of the clouds of dust. So let's take a look at some of the science questions, some of the frontiers in astronomy that we will be able to address using the infrared capabilities of the James Webb Space Telescope. So one of the key questions is, what precisely caused the first stars and galaxies in our universe to form? So we currently believe that around 1 billion years after the Big Bang, or sorry, actually this was a couple hundreds of millions of years after the Big Bang, the universe was largely opaque. Essentially, whenever a star or galaxy emitted high energy light, it was immediately absorbed by hydrogen atoms in the universe. So the universe effectively was opaque. Light couldn't spread outwards. And this is very different from what we see in the universe today, where we can see stars and galaxies that are hundreds, millions, or billions of light years away. So there must have been a period of transition between the universe being opaque and being transparent, which is an era that we call the era of reionization. So we have a good theoretical understanding of how this took place, where essentially transparent bubbles grew around the first stars and galaxies. As they emitted more and more ultraviolet light, it ionized hydrogen in our universe, producing a plasma between the stars that is transparent. And eventually these bubbles grew until the whole universe was transparent. But we don't yet observationally know the exact timeline in which this took place. So by observing the first stars and galaxies, we want to observationally probe how and when this transition occurred. It will also be interesting in its own manner just to discover the very first galaxies that formed, to look at the shapes of those galaxies and compare them to galaxies in our nearby universe. So here, for example, is an image of one of the most distant galaxies we have seen to date, called GNZ11, that formed around 400 million years after the Big Bang. So for galaxies, the idea with Webb will be to effectively produce a picture book showing young galaxies, kind of teenage galaxies, mature galaxies, and old galaxies in our local universe, to see how galaxies formed and changed over time, using the fact that the universe is essentially a time machine. Webb will also tell us about the center of galaxies, in particular about the processes in which the supermassive black holes at the center of galaxies interact with their surrounding galaxies. So in our own galaxy, the Milky Way, Webb will be able to closely examine stars orbiting around the black hole at the center of our galaxy, which is called Sagittarius A star. And by measuring the speeds of the stars around the black hole in our galaxy and other galaxies in the nearby universe, we will be able to weigh how heavy these black holes are. And we will also learn about black holes in the distant universe, which was a far more chaotic and energetic era. So in this artist concept, what we're seeing is an object called a quasar, which is essentially a black hole that has a disk of gaseous material, for example, from stars that it is devouring, falling onto the black hole. And as the gas falls onto the black hole, it heats to incredibly high temperatures and produces these jets of X-rays that come out of it. So we hope to study quasars from the distant universe in the infrared to try and understand how important black holes are for the formation of the very first galaxies. And moving down to smaller objects, by studying these essentially stellar nurseries, these clouds of dust where stars are currently forming in the infrared, so we can directly see these very young stars and disks where planets are forming around these stars. We want to put a precise timeline on the process of stellar formation and planet formation. Another really important thing that we can do in studying these clouds of dust and gas in space is not just to see the stars that are forming, but by measuring and observing this gas in a wide wavelength range, we can look for the specific chemical fingerprints of particular chemical species, like molecules and atoms. So we will not only be able to see where the dust is, we will be able to precisely measure the chemical composition of the initial material that forms stars and planets. And speaking of planets, getting on to the area that my own research is focused on, and I'll be happy to talk much more about this going off on tangents in the questions afterwards. We are going to learn a huge amount about the planets in our own solar system and also planets around other stars using the Webb telescope. So Webb will be able to observe all the planets in our own solar system from Mars and further outwards, because it can't point inwards towards the sun due to its sun shield. And because it is observing in the infrared, it will be able to peer below the top cloud levels of objects like Jupiter, shown here, and observe the deep weather systems at play inside the gas giants. It will also be able to measure cloud and dust storms in the atmospheres of Mars and have a lot of great applications there. But perhaps one of the areas that the James Webb Space Telescope will have the biggest impact is on measuring the composition of planets around other stars. So I will be using the Webb telescope to conduct a technique called transmission spectroscopy. I'll just replay the animation. The idea is that when a planet passes in front of a star, if we observe this planet at a wavelength where the atmosphere is opaque, because there is a molecule that strongly absorbs that color of light, the planet essentially appears to be slightly larger. It obscures more of the light from its host star, as shown by this orange ring here. If instead we observe a color of light where the atmosphere is transparent, the planet will appear to be slightly smaller. So by measuring how the amount of light absorbed by the planet changes as a function of wavelength, and comparing this to laboratory experiments and theoretical calculations, we can precisely measure which molecules and atoms are in the atmosphere of this planet. And depending on the type of planet we observe, there are many different questions that we'll be able to address. Many of the planets that I have been involved in studying to date are giant planets that orbit far closer to their star than Mercury. So since we're not the most creative with our naming, we hence call these hot Jupiters. They have temperatures of a couple thousand Fahrenheit typically. And at these high temperatures, truly exotic chemistry takes place in these atmospheres, unlike anything we have in our own solar system. So we have detected molecules such as titanium oxide and vanadium oxide in these atmospheres. So things that we usually think of as rocks on the Earth can exist in the form of mineral clouds and rain in these atmospheres. So imagine a planet where it has clouds of emeralds and sapphires that rains liquid iron, for example. These are truly exotic worlds. We will also be looking at planets similar to Neptune in our own solar system, which are especially good indicators of the process of planet formation. So planets like Neptune and Uranus, they accreted lots of cometary material when the solar system formed, meaning that they're very rich in things like water vapor and methane that comets are mainly made of. So by measuring how much water is in the atmosphere of Neptune mass exoplanets, we hope to be able to undertake a statistical survey of how planets form for many different types of stars. But we won't just learn about the formation of planets. An area of research that I will be leading using the Webb telescope will be looking at what happens to planets after their stars die. So I have a program that will be observing the first planets that we have found around a white dwarf star, which is the leftover core of a star like our own sun. By measuring the composition of this planet, my team and I will be trying to figure out what will happen to planets like Jupiter and Saturn after our own sun dies many billions of years from now, which could also indicate to us what the long-term fate of the Earth will be many billions of years in the future. And perhaps the area that has most people excited about exoplanets is that the Webb telescope will be the very first time that we will have a telescope sensitive enough to search for signatures of life on rocky planets around other stars. The collecting area of the Hubble Space Telescope was just not enough to be sensitive enough to these biosignature molecules. And in the infrared, molecules like ozone and methane that on the Earth are strong signatures of life can be detected. So we're very excited to be beginning as soon as July of this year, looking at rocky planets for the first time and gradually starting over the course of the next few months and years to do a survey looking for signatures of life on planets around other stars. So in the last 7 or so minutes of my talk, I will just briefly touch upon some of the engineering aspects behind the telescope that make all of that science possible. So the Webb telescope consists of a large segmented mirror that we see just coming into view here, and a sun shield at the bottom that blocks out stray sunlight. It's a much larger telescope than the Hubble Space Telescope. So while the primary mirror on Hubble is around about 2 meters in diameter, Webb is 6.6 meters. And that gives it a much greater sensitivity in that it doesn't take us long to obtain a given precision on our observations. So the collecting area helps us, and the wavelength range, as we heard earlier, is also crucial to the science. And Webb didn't just come out of nowhere. Although it finally launched on Christmas Day last year, this is a telescope that's been in the planning since 1989. It just illustrates the huge timescales involved in designing space-based missions in astronomy. So here are some of the images from the final testing that took place when the telescope's mirrors were folded up ready to be packed onto the Ariane 5 rocket prior to its launch. Incidentally, the reason why the mirror had to be segmented into a number of different hexagonal tiles instead of a circular mirror like Hubble is because there actually aren't any rockets around today that have a large enough payload fairing to fit the entire telescope in. So Webb had to be folded up like origami just to fit inside the 5-meter payload fairing of the Ariane 5 rocket. So each of these mirrors also need to be cooled to incredibly low temperatures, around minus 390 Fahrenheit. And many materials don't retain their strength at those low temperatures. So the mirrors are mainly made of an alloy of beryllium with a thin coating of gold, only about 1,000 atoms thick on the top, because gold is a very efficient reflector of infrared radiation. So when the light from a star comes into the primary aperture of the telescope, it is then dispersed through 4 different infrared instruments that then split up the incoming white light into a spectrum that then will range everything from about 600 nanometers, so kind of greenish colored light to reddish light, all the way through to the infrared. And by dividing the light up into the full rainbow and beyond, we can then search for which colors of light are missing. And that is what ultimately tells us about the chemical composition of objects in the universe. So if along the way to reach us, a certain molecule strongly absorbs certain wavelengths of light, we then won't receive as much of that color of light. So this is the characteristic chemical fingerprint that can tell us what an object is made of. So right now, Webb is at a point far beyond our moon called the L2 Lagrange point. This is a sweet spot where the gravitational pull of the sun, the earth, and the moon roughly cancel out, and Webb executes a small orbit around this point. It's a great location to be. It doesn't have many of the problems that the Hubble Space Telescope in low Earth orbit has. Perhaps the most obvious one being that half the time the Earth is in the way with Hubble, so we actually get twice as much observing time by going out this far. You'll also see that the telescope is pointed down with the sun shield facing the sun. And that's because we want to keep the mirrors and instruments incredibly cold. Otherwise, if the telescope was hot, when we looked in the infrared, we would just see the heat radiation from the mirrors themselves and not the stars and galaxies that we are looking at. Since the telescope launched on Christmas Day, it has now completed its unfolding sequence, and remarkably, everything went completely according to plan without any incidents, even though something like this had never been attempted before. So truly an impressive feat by the engineering teams that spent so long working on this. And another really important thing is that the injection orbit by the Ariane 5 rocket was actually so efficient that it has dramatically increased the expected lifetime of the telescope. Many of us were planning for a 5-year operational mission. And the latest estimate that we've heard is that it actually has enough fuel to last for 20 years. So perhaps the rate limiting step will be how long the instruments on board the telescope stay operational. But that's a dramatic increase in how much science we'll be able to get out of the mission over the decades to come. So this again is just illustrating the setup of the telescope. And one of the last things that I want to show is one of the first images taken by the telescope. So this is not the final product. This is still a calibration image that was taken about a month ago. But what this shows is that all the mirrors on the telescope are now correctly aligned. And what's particularly striking here is that although this image was just focusing on a particular star here, you can see entire galaxies. You can even see, if you zoom into like a high resolution version of this image that you can find in the NASA press release, the spiral arms of these galaxies. The image quality has exceeded expectations and is only going to get better as the commissioning period winds down over the next few weeks to month, with science operations beginning at the end of June. So to conclude, the Webb Space Telescope is going to contribute to many current frontiers in astronomy. We'll be able to answer questions about how the first stars and galaxies formed in our universe, how galaxies have evolved over the billions of years since then, how stars are born, what the material they are formed from is made of, what will happen to stars and planets after the death of their star. And for the first time, we will be able to observe rocky planets around other stars and search for signatures of life in their atmospheres. And with that, I'll be happy to take any questions.
Remember, everybody, that you'll need to turn your mics back on. And Ken, do you want to put us back to multi-view?
So to start with, I have sort of an elementary question. How does one determine how many light years away a star or other object is?
So it's actually a kind of tricky question because it depends on the distance. So for very nearby objects, you can use a technique called parallax. So essentially, as the Earth orbits around the sun, when you're at one end of the orbit, you can look at the star, and then 6 months later, you can look at the star. And there will be a tiny change in where the star appears to be on the nighttime sky. So by measuring the angular change in where the star appears on the sky, just using trigonometry, you can work out how far away it is. So that can be used for very nearby objects. For the complete other extreme, like objects in the very distant universe, like supernovae and galaxies billions of light years away, we can use what are called standard candles. So if you have an event like a supernova, there's a class of supernovae called type 1a supernovae that form when a white dwarf star that is gradually accreting mass onto it reaches 1.4 times the mass of the sun, and exactly at that mass, it explodes. And since we know exactly what the mass of this exploding star was, we know what the brightness of it should be. So by comparing how bright it appears to be where we observe it at Earth to how bright we know the object intrinsically is, we can work out how far away it is. And there are many intervening steps as well. We call it the distance ladder. So we calibrate things based on when we can measure the distance to some objects by 2 or 3 different techniques. And that's how we're able to work out how many light years away both nearby and distant objects are.
Interesting.
I like the fact that you're still using standard candles. Okay,
yeah.
my question is there any theoretical limit to the lifetime of the Webb telescope?
Not really. It will depend on the quality of the engineering, which from everything we've seen so far has gone pretty much according to plan. So there is the 20-year life frame that would come from just the fuel reserves that are on board. And then after that, you wouldn't be able to do the fine maneuvers that are needed to keep it in its orbit. So while there were telescopes like Hubble that were designed to be serviced, so the space shuttle went up a few times to fix the Hubble Space Telescope and to add new instruments to it, Webb was not designed for servicing, but I do know that there are some discussions taking place at NASA at the moment, given that it looks like it could last for 20 years and not 5 years, about the possibility of developing a mission that maybe 10 or 15 years from now might be able to go out and refuel it. But it's very, very early days for that. So if you could go out and do a servicing mission 15 years from now, you might be able to extend the mission's lifetime for many, many decades beyond that.
So with regard to fuel, how much of the fuel is, I presume there must be some atomic reactors of some sort on it, and how much is solar energy that is being used?
So it's all just chemical reactant that is on board for just the tiny maneuvering thrusters to keep it in its orbit. It doesn't require much fuel because the Lagrangian point is a gravitational sweet spot. It just needs small correction burns every now and then. And of course, to rotate it as well to look at different objects. So it is entirely solar powered. I don't know the exact figures for like how many
Okay.
watts and things it is, but yeah, it does have solar panels to power it.
Does it have mechanical pieces on it that might wear out?
Yes, and so many people expect that those potentially could be the rate limiting step that could cause an instrument to fail even before the fuel runs out. But that would be a kind of thing that if you can eventually get out a servicing mission 10, 15 or so years from now, you would then be able to fix and replace that instrument. So for example, the Kepler Space Telescope that has found thousands of exoplanets and ran for many years until the reaction wheels on board it failed. And at that point, it couldn't stably point at objects and the mission was discontinued at that point. Although for a time, some of the reaction wheels had failed, but the engineers were able to compensate for that using the radiation pressure from the sun, which was a very clever and ingenious solution. So yeah, mechanical failure could be the thing that will be the rate limiting step, but all the instruments are guaranteed for at least 5 years with a target minimum 10-year lifetime.
Brian, you said the mirrors had to be cooled. Isn't space cool enough? Well,
so yeah, space is pretty cold, but some of the instruments need active coolant on board to actually, because when it launches, obviously, just from the it's not the temperature, background temperature of space. It will take pretty much infinite time to cool down to that. And also there's heat being generated via light from the sun that is falling on it and just via the operation of the instruments. So yeah, I'll have to remind myself of the exact operational temperature because I do have that. Wait a moment, let's see. Yeah, so the operational temperature is 40 Kelvin, which, yeah, it's warmer than the background temperature of space. But we need to precisely cool it down to make sure that it's exactly at the operational temperature. And we can't just kind of wait for it to reach the temperature of the background universe. And there are actually some graphs somewhere that NASA have been putting out showing kind of the temperature so far as a function of time. And you can precisely see when the coolant kicks in. I'll see if I can find one of those because they're quite interesting. I'll be happy to take another question in the meantime.
Brian, how is the information gathered by the telescope distributed? Is it open to all astronomers that are interested? Is it a select few like you? Who gets this information?
Yeah, that's a great question. So all data obtained by the telescope will eventually become publicly available. The timescale does depend on the particular program. So data like the White Dwarf Planet program that I'm leading is what's called a small program. So I was asking for less than 25 hours of time on the telescope. If you have a small program, you get proprietary access for 1 year to the data, and then it becomes automatically publicly available after that. Large programs that have requested more than 75 hours on the telescope become public instantly as soon as they are observed. So all data will be public eventually, and we're completely transparent on what the telescope will be doing. There is a list of programs that you can look up, and I'll just get that up now, kind of showing. So there are a series of guaranteed time observations. So people that spent years and years and years of their life working on the telescope were rewarded for that work with many hundreds of hours of guaranteed time. So I am involved in some of these programs that will be looking at exoplanet atmospheres with the different instruments. But in addition to this, most of the time that was available in the first year of operations was open to any astronomer in the world could apply for time. So that is how, for example, I got the time for my White Dwarf Planet proposal. So if I go down to exoplanets, search myself, here you can see my program, for example, which will have 13 hours on the telescope. So anyone on the planet can apply for time on the telescope. There is then a peer review process that takes place over a couple of months or so, which is all done in a dual anonymous mode. So we don't know who the referees are, and our names are taken off the proposal, so they don't know who wrote it either. So yeah, anyone in the world can apply for time on the telescope. Technically, you don't even need to be an astronomer to do it. You would just need to, but since you need to pass like the peer review process and things, in practice, everyone is an astronomer.
I have a simple question. Who manufactured all the glass and assembled the telescope? Was it Corning like many in the
No,
past?
it's not glass. It's beryllium with a gold coating.
Well, yeah,
It was Northrop Grumman that was the main contractor.
Grumman. So complete change in technology of the mirrors.
I
Impressive.
mean, there's a reason why it took so long to take place. It was, I remember during my PhD, I was being told in 2018, at the end of your PhD, it'll launch and you'll be able to analyze the first data. And I know people who were doing their PhD in like 2010 or so, who were also told they'd be working on data by the end of their PhD. It just kept being pushed back and back and back because it's the most complicated thing we've ever put into space before. And it's amazing that it just worked on the first try without any issues whatsoever.
Are there many other Cornell projects that have been allocated time?
Yes, yeah, plenty. Even in the guaranteed time. So my advisor, Professor Nicole Lewis, she has a whole 3 different programs in guaranteed time that will be looking at a hot Jupiter, a Neptune-like planet, and a rocky planet in the habitable zone. And I'm actively involved in all of those efforts as well. Jonathan O'Neill has guaranteed time as well on a number of different exoplanet and disk programs. So yeah, Cornell is heavily involved.
Ryan?
Yep.
I noticed that exoplanets are right at the top of the list that you showed before. And I'm just wondering how many rocky exoplanets are going to be in range? What number do you anticipate being able to look at carefully?
So I don't know the number off the top of my head. I mean, even in the first year, there's probably between 5 and 10. No, closer to 10 rocky planets will be looked at just in the first year. They're not all in the habitable zone. Some will be more like Venus-like planets, and some we're observing are even what we call lava worlds, so about 2,000 to 3,000 Kelvin or so in temperature with molten surfaces. So the issue with the habitable zone planets is that the signals are so small compared to giant planets, because the characteristic size of the atmosphere is smaller for rocky planets due to their lower temperature and the higher weight of molecules like nitrogen and oxygen, which means that it takes a lot more observation time to get precise observations of rocky planets than giant planets. So in terms of the number that we will get detailed characterization of, we're probably only looking at about 5 or so habitable zone rocky planets. Over the next 5 years, we'll get detailed characterization purely because of the long time that it takes. But given the extended lifetime of the mission, we know of plenty more potential targets, but just some more favorable than other ones. So it will probably be that you'll keep seeing in the news headlines the same planets being repeated time and time again, so we make new discoveries for those planets, purely because we already know in advance what some of the best targets are.
Thank you.
We'll have to wait for future missions to then do a statistical survey of thousands or so of planets, but those missions are all on the drawing board and being planned at the moment.
Thank you.
What would be the next telescope to launch, or the next significant observational device?
Well, it depends on the particular area of astronomy, because there are many different things being developed for different wavelength ranges. In my own field, probably one of the next significant ones will be the Ariel mission, which is a European mission that should be going up in 2029. That will be aiming to do a survey of 1,000 exoplanet atmospheres, ranging from giant planets down to super-Earths, and actually give us a statistical census of what planetary atmospheres are like. We've only been able to observe about 50 exoplanet atmospheres to date, so 50 to 1,000 will be a huge leap forward. And NASA are still thinking about what the next thing will do. A decadal survey just came out that recommended to NASA what to work on next. So the next really big thing as a general astronomy telescope, they haven't come up with the exact name for it. It's just an acronym. It's like the Optical UV IR Large Telescope. This would be a telescope that would be designed with the main scientific goal being to directly image an Earth-like planet around a sun-like star, and using reflected light, look for signatures of biological gases and even for reflection from the surface. So if the planet was like the Earth, you would be able to detect chlorophyll, for example. So, but that's probably not coming until the 2040s. It takes a very long time to develop these missions, as we've seen with the Webb telescope.
Well, it's 2:08. Do we have any other pressing questions? Otherwise, we probably should let Dr. MacDonald go. Excellent presentation, very interesting. Thank you so much.
Thank you.
having
Thank
me.
you.
Yes, I feel much more informed.
And just keep an eye out. There's going to be so many press releases that will be coming out in the second half of this year with the initial discoveries. And we're going to be working manically to get the results out as soon as we possibly can.
Great.
Thank you very much.
Yes.
Thank you.
Thank you.
Very good.